Hello, my name is Keti Korini, and I'm a PhD student in the Data and Web Science group of the University of Mannheim. I'm going to be discussing the topic of column type annotation using ChatGPT. Column type annotation is a subtask of table annotation, where the goal is to annotate columns of a table with the semantic type of the values that are contained in each column. Some examples of column annotations can be seen on top of each of the columns in this example table. For example, by looking at this first column of this table, we can see that the cell values represent the names of some restaurants. Therefore, the semantic type that can be assigned to this column is restaurant name. Usually, this annotation is done using a predefined set of semantic types. It is an important task as it is considered important for data search as well as data integration in the context of data lakes. There have been many works that have been proposed for CTA. Some line of works focus on linking the entities found in the cells of the columns to entities in some knowledge graph. And by looking at the type of these entities in the knowledge graph, they choose the semantic type of the column. Other line of work build custom deep learning frameworks, such as in the case of Sherlock. And lastly, some works fine-tune pre-trained language models, such as BERT and Roberta. And in this category, we find the state-of-the-art method for CTA, which is Dodo. However, there are some disadvantages related to these deep learning-based methods. Firstly, they require a significant amount of training data to reach a good performance, and they mostly tend to not generalize well to unseen entities or different value formats. Large language models, like recent GPT models, could offer to help overcome these disadvantages. They could potentially require less training data and could be more robust to unseen entities or formats. In this presentation, I will introduce how we have explored the potentials of using ChatGPT for the CTA task. I will present how we have studied different prompt designs with instructions in context examples and using message roles. We additionally propose a two-step pipeline to help with the large label space problem. Finally, we compare the performance of ChatGPT to a fine-tuned Roberta model and to Dodo. The training and test dataset that we used for our experiments were downsampled from the schema.org table annotation benchmark, where we chose tables from 4 different domains. The 5-label set contains 32 semantic types that are, for example, restaurant name, price range, address region, etc. Our training set consists of 62 tables, and our test set consists of 41 tables. The LLM that we used is the GPT 3.5 Turbo, the 1st of March version. We also set the temperature to 0 so as to decrease the randomness of the answers from the model. We start our experiments by designing some simple prompts and 3 different ways of introducing the CTA task to the model. The first way of presenting CTA to ChatGPT is by introducing CTA as a column type classification problem. The columns in this case are passed one by one to the model to be classified. For example, to classify this last column of the table, we ask the model to classify the given column into one of the following types, where we list all 32 semantic types. Then we pass our column input, where we concatenate the values of the first 5 rows of the column, and we expect a type from the model. We call this prompt the column format, and we treat this as our baseline when comparing to other prompt designs that we later experiment with. The second way of introducing CTA to the model is by treating it as a general text classification problem. This format is tested to see if ChatGPT would understand better more general terms like text and class instead of column and types. As with the previous column format, we pass the columns one by one to ChatGPT. The last way of introducing CTA is the table format, where we experiment if ChatGPT can annotate all columns of a table at once. We use the keyword here, table, and pass the rows of the table concatenated one by one. In this case, the model is expected to answer with as many classes as there are columns. Taking a look at the results of these 3 simple prompts, we see that we have quite average results. The column and text formats are quite close to each other, but on the other hand, the table structure is not understood and shows a decrease of 7.95% compared to the baseline column format. With the goal of providing some reasoning steps to the model, we continue our experiments by using the same 3 prompts as before, but now adding some instructions. In the case of the table format, we specify to the model that the input is a table, so it needs to make a table out of the input. If we take a look at the performance, using instruction greatly helps all 3 formats, but the largest increase can be seen in the table format, where we have a 34% increase. The next step in our experiments was to explore the usage of message roles. Instead of passing now to the model a simple prompt that contained all the tasks and instructions in a block of text, we provide the information into, we divide the information into messages and give each of these messages a different role. So there are 3 different message roles that are provided by OpenAI models: system, user, and AI message. So we pass as system messages the task and the instructions, and using a user message, we pass our input. We then wait from the model an AI message where the column types are contained. Looking at the result, using these message roles instead of simple prompts increases again the value of F1, and the table format now is achieves 39% more than the baseline. In the next step, we experimented with showing different number of demonstrations to the model. This can be done by using user and AI messages to simulate a conversation. In order to simulate a conversation between the user and the model. In this slide, the demonstrations are shown in these orange boxes. As we increase the number of demonstrations, generally the performance of ChatGPT increases. We observed here that there is a 3% increase in the table format case compared to its zero-shot case. As a final step to our experiments, we explore the idea of splitting CTA into 2 steps. The first step would predict the domain and type of the complete table, and in the second step, CTA is performed using a reduced set of labels that will belong to the predicted domain in the first step. As an example, to the first step, we would ask the model to classify an input table into one of our 4 domains. After the model has replied with the domain, which in this case is restaurant, in the second step, we only show to the model 11 out of the 32 labels, which belong to the restaurant domain. The advantages of this is that the token space can be saved for datasets that have large vocabularies, and it also helps in simplifying the annotation task as the model chooses from a smaller set of labels. We tested this 2-step pipeline into in a 0, 1, and 4-shot setting. A 0-shot 2-step approach is slightly better than the 5-shot single-step approach, which was at 88.83. We compare our best approach to 3 methods. Firstly, a random forest classifier using TF-IDF features. Secondly, a fine-tuned Roberta using the concatenated cell values. And thirdly, the state-of-the-art method Doduo, where the input is serialized tables. By running experiments with different numbers of shots, we can see that compared to the 0-shot 2-step pipeline, all methods perform worse, except for Roberta when it is trained with 356 examples, which reaches quite a similar performance. Doduo's performance increases when trained with more examples. However, when fine-tuned with 1,600 examples, it still performs lower than the 0-shot ChatGPT 2-step pipeline. In conclusion, by instructing the model and breaking CTA into a 2-step pipeline, ChatGPT achieves a good performance of 89%. In order for a Roberta model to reach a similar performance, it needs to be fine-tuned with 356 training examples. Finally, we showed that the 2-step annotation pipeline helps with reducing token numbers, which helps with the cost of the API usage and simplifies the annotation task by showing the model only a subset of the full label space. Thank you for listening.